A doctor can't quite pinpoint an illness.
An algorithm has no idea where the market is going.
A meteorologist isn't sure where the storm will land. See, our world is just filled with this kind of uncertainty, right? It's this giant web of interconnected causes and effects that we're always struggling to untangle.
The world is random, but your decisions shouldn't have to be. So what if you had a kind of mathematical key to unlock these really complex real-world problems?
Well, that key actually exists. Today, we're diving into Bayesian networks. They're this incredibly powerful probabilistic model that helps us see the hidden connections in the world and, honestly, predict the unseen with some stunning accuracy.
So, the core challenge that pretty much everyone faces, from data scientists to doctors, is just making sense of a world where everything feels connected, but all the relationships are, well, they're foggy. We've got bits and pieces of information, but how do they all influence each other?
And here is the solution. Now, it might look pretty simple, but this is a Bayesian network, and it literally turns that chaos into a clear map. You can see right here that the chance of rain and whether the sprinkler is on both directly influence if the grass is wet. And that, in turn, can lead to potholes or a slippery road. It's a logical, visual model of how things actually work.
And this isn't just some theoretical diagram you draw on a whiteboard. It's a dynamic engine for reasoning. Bayesian networks are used absolutely everywhere to master probabilistic thinking and handle that messy real-world uncertainty we talked about. They're used to predict everything from medical diagnoses to stock market volatility and even to figure out which of your emails is spam.
Okay, so let's dive in and see how these powerful tools are actually put together. What are the fundamental pieces that let them model the world so effectively?
Now, what's really interesting about this is how it shows the network is built in layers, from the ground up. Down at the bottom, you've got the basic building blocks, the random variables, or nodes. And then as we move up, we start adding the structure and then the math, building a complete picture of the system.
So that first layer of structure is what's called a directed acyclic graph, or a DAG for short. Just think of it like the skeleton or the blueprint of the whole network. The nodes are the things we care about, like rain or sprinkler. And the arrows, well, they show a direct causal influence. Rain causes the grass to be wet. And it has to be acyclic, which is just a fancy way of saying you can't have feedback loops. An effect can't circle back and cause itself. Okay, so if the DAG is the skeleton, then the conditional probability tables, or CPTs, are the muscles. This is where we put hard numbers on those relationships. For each item, a CPT answers a pretty simple question. If I know the causes, how likely is the effect? So, for example, a table might tell you there's a 90% chance the grass is wet if it's raining. This is where the network gets its real predictive juice.
So, we've built the structure. Now, let's see how it actually works. I mean, having the map is one thing, but using it to navigate, that's where the magic really happens. This is all called probabilistic inference, basically using the network to think.
This flowchart shows you the whole process. When we get a new piece of information, like we observe some new evidence, the network doesn't just sit there. It runs what's called an inference algorithm to update its beliefs about everything else in the system. It's literally using what you now know to calculate the probability of what you don't.
So let's just walk through a quick example. Step 1. You wake up, look outside, and you observe the grass is wet. Okay, that's your evidence. Step 2. The network's inference algorithm kicks in. Step 3. The network updates its beliefs. The probability that it rained goes up, and yeah, the probability that the sprinkler was on also goes up. Finally, step 4. You can ask the network, okay, given that the grass is wet, what's the new likelihood that it actually rained?
So, here's the crucial point. This isn't just for predicting the weather in your backyard. This ability to reason when things are uncertain has applications that are decoding our world in just countless fields. And this just shows you the sheer breadth of its impact. I mean, in medicine, they're used to diagnose diseases based on symptoms. In finance, they're used to model market risk. In robotics, they help a machine understand its surroundings by fusing data from all its different sensors. Seriously, from cybersecurity to AI safety, Bayesian networks are the engine of modern prediction and diagnostics. But, of course, no tool is perfect. The huge strengths of Bayesian networks are that they're transparent. Unlike a lot of black box AI, you can actually see how they think, which is critical in fields like medicine where you need to trust the reasoning. They also handle uncertainty just beautifully. But they do have weaknesses. Building the structure can be really slow computationally, and those probability tables can get enormous if a variable has too many causes. And like we said, they can't model systems that have feedback loops, where an effect circles back to influence its own cause.
And that brings us to the final thought here. We've seen how these networks can model everything from medicine to markets just by mapping out these hidden relationships. So it's worth asking yourself, if you could apply this kind of probabilistic reasoning to your work or even your life, what's the first complex problem you try to solve?